In this section, we will consider the effects that the transmission network has on electricity markets. We will therefore no longer assume that all generators and loads are connected to the same bus. That means that we will have to consider congestion, constraints on flows, and losses. We will also have to consider two forms of trading: bilateral or decentralized trading, and pool or centralized trading. In bilateral or decentralized trading, all the transactions involve only a buyer and a seller. And this buyer and this seller agree on the price, the quantity, and other conditions that they might want to put on the transaction. The system operator does not get involved directly in trading, and its only responsibility is to maintain the balance and security of the system. That means that this system operator will have to buy or sell a limited amount of energy to keep the load and generation balance, and it may also have to limit the amount of power that generators can inject at some nodes if the security of the system cannot be ensured by other means. Let's explore on a very simple example system how bilateral trading might operate. Let's suppose that generator G1 connected to bus A has sold 300 megawatts to load L1 connected to bus B, and that generator G2 has sold 200 megawatts to load L2, which is also connected at bus B. And we have two lines connecting bus A and bus B. Now the prices that have been agreed as part of these transitions between these generators and these loads are a private matter. However, the quantities must be reported to the system operator so that it can check that the security of the system is not going to be impaired. So, if the total capacity of the transmission corridor between bus A and bus B is more than 500 megawatts, there are no problems. If the capacity of the corridor is less than 500 megawatts, then some of these transactions may have to be curtailed. But the question is, which of these transactions should be curtailed? Well, one approach is to use what might be called administrative procedures. And these procedures might consider whether the transactions have been described as being firm or non-firm, or the order in which these transactions were registered, or some historical considerations. Maybe generator G has been selling to load L1 for a long time and therefore feels like it has a historical right to use a transmission system. The problem with administrative procedures is that they do not consider the relative economic benefits of the various transactions, and therefore they are economically inefficient, because the more economically efficient transaction might end up being curtailed. So it would be better to let the participant themselves decide what makes sense from an economic perspective. So one approach would be to say that the participants should purchase the right to use the network range a trade in energy. And this leads to the concept of physical transmission rights. And those physical transmission rights are intended to support the actual transmission of power over a given link. So let's get back to our example and look at it in a bit detail, including prices, to see how this might work. So let's suppose that G1 sold a 300 megawatt to L1 at $30 per megawatt hour, and that G2 sold 200 megawatt to L2 at $32 per megawatt hour. Now let's suppose that generator 3, which happens to be located at bus B, is willing to sell energy at $35 per megawatt hour. Since generator 3 is connected to the same bus as load L1 and L2, if they buy from generator 3, they would not have to purchase the physical right to use the transmission network. So if we say that the loads have to purchase these physical rights, L2 should not pay more than $3 per megawatt hour for transmission rights, because if you add these $3 to the $32 that it paid to G2 to buy the energy, that would be equal to what it would pay to G3. So if it had to pay more than $3 per megawatt hour for transmission rights, it would rather buy this power from generator 3. Similarly, N should not pay more than $5 per megawatt hour for transmission rights, because that, if you add that to the $30 per megawatt hour that it paid for energy, that would be not as good as buying directly from G3. So this matter, in theory, would give us a way of putting a value on the use of the transmission network. However, there are problems with these physical rights. There are actually two types of problems. One comes the fact that in a transmission network there are parallel paths, and another problem comes from the fact that it's possible to exercise market power with physical transmission rights. Let's start with a problem related to parallel path. Let's suppose that we inject a certain amount of power P at node 1 in a network and extract this amount of power P at node 2. And let's suppose that there are two paths to this network. Path A with a reactance XA and path B with a reactance XB. In this example, I only consider reactances because it makes the whole thing a bit easier to look at, but it could easily be generalized to more complex impedances. This power P that flows from node 1 to node 2 is going to divide itself in a flow FA through path A and a flow FB through path B. The flow FA is given by the ratio of XB, the reactance of the opposite path, and divided by the XA plus XB, the sum of the reactances of the two paths, and multiplied by the power P. Similarly, the fraction of the power that flows 1 to 2 in path B is equal to XA over XA plus XB times P. And you can easily check that FA plus FB is equal to P. Let's apply this to a small 3-bus system. The system is shown on the left of the slide, and the data about this system is given on the table on the right. For each branch, I give you the reactance of the branch and the capacity, or the maximum amount of megawatt that can flow in the branch. Let's suppose that a 400 megawatt transaction has been agreed between generator B and load Y. Generator B is located at bus 1 and load Y is connected at bus 3. Now, because we have two parallel paths between buses 1 and 3, one that goes directly between bus 1 and bus 2, the other one that goes through bus 2, that means that some of the flow is going to go through each path. That means that we are going to need to buy transmission rights on every line in the system. So what happens to a 400 megawatt transaction between B and Y? Well, the amount of power that flows along path 1, that's a path that goes from 1 to 2 to 3, is equal to 0.2, which is the reactance of the branch that goes directly between 1 and 3, and the total reactance of the both paths, so that's 0.2, again the reactance between 1 and 3, plus 0.3, which is the sum of the reactances of the branches between 1 and 2 and 2 and 3. So we multiply 400 megawatts by 0.2 over 0.2 plus 0.3, and that gives us 160 megawatts. Similarly, we can calculate the flow that goes along path 2, which is given by 400 megawatt times the ratio of 0.3, reactance of the path 1, divided by 0.2 plus 0.23, which is the sum of the reactances of the passes 1 and 2. And that gives us 240 megawatts. Now, there's a problem with this because this 240 megawatts exceeds the capacity, transmission capacity of the lines joining buses 1 and 2 and 2 and 3. So, taken by itself, this 400 megawatt transaction between B and Y is not acceptable. However, let's suppose that at the same time a 200 megawatt transaction has been agreed between generator D, which is located at bus 3, and load Z, which is located at bus 1. Using the same method, we can calculate how this flow divides itself between path 3 and path 4. So we get 80 megawatts along path 3 and 120 megawatts along path 4. Now, if we have the two transactions at the same time, we can calculate the flows in every branch. And we find out that F12, the line 1-2, is the same as the flow in line 2-3, is equal to flow along path 1 for the first transaction, minus the flow along path 3 for the second transaction, minus because it's going the opposite direction. So that's 160 megawatt minus 80 megawatt gives us 80 megawatt. Similarly, the flow in line 1-3 is the flow for the first transaction along path 2 minus the flow in the second transaction along path 4. So that's 240 minus 120, that's 120 megawatts. So the flows in all the lines are within limits. But that means that we have to consider all the flows at the same time. So these counterflows create additional physical transmission rights, and economic efficiency requires that we consider these rights, otherwise we would be only using a fraction of the overall transmission capacity of the network. However, we said we are operating in a decentralized trading framework, which means that the system operator, which is really the only one that is an independent party that has access to all the necessary information, this system operator is only there to check overall feasibility, not to tell the participants what to do. So these participants really would have to trade the physical rights bilaterally. And in theory, if we have enough participants, well, they should be able to trade efficiently amongst each other, with each other, and the market, these participants, would discover the optimum combination of physical transmission rights and trades, and that would mean an economic optimum. In practice, the complexity and the amount of information involved are such that it's very unlikely that this optimum could be found in time. Physical transmission rights also create problems related to market power. Let's go back to our two-bus example. Let's observe that G3 is the only generator at bus B. Now, we could imagine a situation where G3 would purchase transmission rights from A to B. Now, you may say, why would G3 buy these transmission rights? Well, G3 would buy the physical transmission rights but would not use them or resell them. The consequence of that is that it would effectively reduce the transmission capacity from A to B because G3 would own these rights. Because G3 has reduced the transmission capacity from A to B, it is now able to increase the price at B. It has essentially created a little pocket where it has a lot of market power. Now you could suggest that we could introduce a use them or lose them provision when you buy transmission right, meaning that either you are going to use these transmission rights or somebody else gets to use them. In theory, that's nice. In practice, it would be very difficult to enforce this provision in a timely manner because G3 could pretend until the very last minute that it will be using these physical rights, and then when it's too late, well, it's too late to do anything about it. We have already encountered centralized or pool trading when we were discussing energy markets without considering a transmission network. But it's also applicable to the case where we have to consider the effect of a transmission network. So in a centralized or pool trading framework, the producers and the consumers submit bids and offers to a central market organization, which is run by an independent system operator. This independent system operator would select the winning bids and offers in a way that optimally clears the market, but at the same time respects security constraints imposed by the network. If there is no congestion in the transmission network, and if there are no losses, or if we assume there are no losses, the price across the network would be uniform. On the other hand, if there are congestions or losses in the transmission network, the price of energy will depend on the location where the generator and the loads are connected. Let's study centralized markets using an example that involves two countries, Borduria and Syldavia, and we'll look at the effect that an interconnection has on prices of electricity in these two countries. So we will assume that each country has an electricity market and that there is perfect competition within each country. And we will also assume that these two countries each have their own electricity grid, which is very strong, meaning there is no congestion or losses within each country. So we will make the assumption that there is a single price for electrical energy in Borduria and a single price for electrical energy in Syldavia. And because there is perfect competition within each country, this price will be equal to the marginal cost of production in that country. Let's look at the price of electricity in each country when there is no interconnection between the two countries. Let's suppose that some studies have been done and I have checked that the marginal cost of production of electrical energy in Borduria, MCB, is equal to 10 plus 0.01 times the production is in Borduria. And because we assume that we have perfect competition within the electricity market of Borduria, this is also the price of electricity in Borduria. If the load in Borduria, the demand in Borduria is 500 megawatts, then the price in Borduria is going to be 10 plus 0.01 times 500 is $15 per megawatt hour. Can do the same thing for Syldavia with the same assumption. The price in Syldavia is equal to the marginal cost of production in Syldavia, and studies have shown it's 13 plus 0.02 times the production in Syldavia. And if the demand in Syldavia is 1500 megawatts and is met strictly by generators in Syldavia, we have PS is 1500 and the price in Syldavia is $43 per megawatt hour. So we can observe that the generation in Borduria is cheaper than the generation in Syldavia, and as we would expect, the price in Borduria is significantly lower than the price in Syldavia. So what we want to look at is the economic effect of an interconnection on these electricity markets. We're not going to be looking at whether or not an interconnection should be built. We assume that the line is there and we are looking at what effect it has on the prices. So how might things work out if there is an interconnection between Borduria and Syldavia? Well, if you recall, generators in Borduria are cheaper than generators in Syldavia. So one thing that we might want to try is to whether we could produce all of the demand for both Borduria and Syldavia by the generators in Borduria. So that means that PB, the power produced in Borduria, would be 2000 megawatts, which is the sum of the demand in Borduria and the demand in Syldavia. And the power produced in Syldavia at PS would be 0. But if we put that in the expressions for the marginal costs in the two countries, we come to the conclusion that the marginal cost in Borduria would then be $30 per megawatt hour, while the marginal cost in Syldavia would be $13 per megawatt hour. And that doesn't make sense, because at that point the generators in Syldavia could sell at a lower price than the generators in Borduria, and this situation would not be tenable because it would not be a market equilibrium. So what we need to find is a market equilibrium. Well, market equilibrium would mean that we have the same price in Borduria and in Syldavia, and that demand would be satisfied. In this case, we have assumed that the demand does not change with the price, so we must have that the in Borduria plus the production in Syldavia must be equal to the demand in Borduria plus the demand in Syldavia, which is 500 plus 1500 is 2000 megawatts. Now we also have the expressions for the marginal cost and the price in both countries, so putting all of that together and in these equations, we find that the price at this market equilibrium would be $24.3 per megawatt hour, and that would mean that we should be producing 1433 megawatts in Borduria and 567 megawatts in Syldavia. Now, if we produce 1433 megawatts in Borduria and the demand in Borduria is only 500 megawatts, that means that we have 933 megawatts that flow from Borduria to Syldavia. That's what we represent by FBS. Or we can do the calculation the other way around and say that if the demand in Syldavia is 500 megawatts and the production in Syldavia is only 567 megawatts, the missing 933 megawatts are imported from Borduria on this interconnection. We can visualize what's going on with the following diagram. Let's plot first the supply curve for Borduria. And we see that if Borduria produces 1433 megawatts, the price will be $24.3 per megawatt hour based on the marginal cost of producing this power in Borduria. Let's plot then on the supply curve for Syldavia, but let's invert the x-axis. And so we measure from the to the left, and if the supply curve for, if the amount of power produced in Syldavia is 567 megawatt, then using the supply curve for Syldavia, we find that it also leads to a price of $24.3 per megawatt hour in Syldavia. Now, 1433 plus 567 is equal to the total demand in Borduria and Syldavia, which is 2000 megawatts. But we can also divide this in 500 megawatts of demand in Borduria and 1500 megawatts of demand in Syldavia. And in between, we have the flow between Borduria and Syldavia, which is 933 megawatts. Now, so far, we have assumed that the interconnection could carry whatever power we wanted to flow from Borduria to Syldavia, whatever amount of power was dictated by the market to create a market equilibrium. What we need to look at now is what happens if there are limits to the amount of power that can be transmitted between Borduria and Syldavia. For example, let's assume that the interconnection was designed to be able to only 400 megawatts. Well, that means that the power produced in Borduria is limited to the 500 megawatts that are consumed locally and the 400 megawatts that can be exported to Syldavia for a total of 900 megawatts. Similarly, the power produced in Syldavia is equal to the load in Syldavia, 1500 megawatts, minus the 400 megawatts that can be imported from Borduria for a total of 11 megawatts. If we put these numbers in the marginal cost curves for Borduria and Syldavia, we get that the marginal cost in Borduria is 10 plus 0.01 times 900, or $19 per megawatt hour. Now, because we have assumed that we have a perfectly competitive market in Borduria, that is also the price in Borduria. Similarly, the price in Syldavia is given by the marginal cost of production in Syldavia, which is 13 plus 0.02 times the 1100 megawatts that are produced in Syldavia, or $35 per megawatt hour. So we observe that because there is a limit to the amount of power that can be transmitted from Borduria to Syldavia, a price difference arises between the two locations, and therefore we have what's called locational marginal pricing or nodal pricing. Locational pricing because the price depends on the location, marginal pricing because in both locations the prices are based on the marginal cost of production. We can visualize what happens by going back to our diagram. And we did not have any limits on the amount of power that could flow from Borduria to Syldavia. The price in the single market was given by the intersection of the supply curves in the countries, and that was the intersection of the red curve and the green curve. In this case, because we put a limit on the amount of power that can be exported from Borduria to Syldavia of 400 megawatts, we see that we get a difference of $16 megawatt hour in between the prices in the two countries. The table on this slide summarizes the results that we get with these different markets. So let's start with the case where we have separate markets. That I mean that we have no interconnection between Borduria and Syldavia. In that case, the power produced in Borduria, PB, is equal to the demand in Borduria, and it's 500 megawatts. We have seen that in that case the price in Borduria is $15 per megawatt hour, and therefore the generators in Borduria collect a revenue RB of 7,500, which is 15 times 500. The consumers in Borduria pay an amount EB, which is also 7,500, because it's also 15 times 500, the demand in Borduria. In Syldavia, on the other hand, the production is 1,500 megawatts, because it's a load in Syldavia. The price we've seen is $43 per megawatt hour. So the revenue per hour for the generators in Syldavia is 43 times 1,500, or 64,500, which is also the amount that the consumers pay in Borduria for their electricity. The flow from Borduria to Syldavia in this case is 0, so FBS equals 0. If we add the total revenues of the generator in Borduria and Syldavia, we get 72,000, and that's also equal to the total amount that the consumers pay in Borduria and Syldavia. The next thing that we need to consider is a single market where there are no limitations on the amount of power that flows through the interconnection. In that case, we saw that the Bordurian producers at this market equilibrium would produce 1,433 megawatts, and that the price in this single market would be $24.3 per megawatt hour. So the Bordurian generators would collect a revenue RB of 24.33 times 1,433, which is 34,865. The Bordurian consumers would pay the Bordurian price, which is a single market price in this case, 24.33 times the demand in Borduria, which is still 500. So they would pay 12,165. In Syldavia, the Syldavian generators would produce 567 megawatts only. The price in Syldavia would be the price in Borduria, and would therefore be $24.33 per megawatt hour. the revenue of the Syldavian generators would be 13,795, which is a price 24.33 times the production of the Syldavian generators, 567. The Syldavian consumers would pay 36,495, which is the price of electricity in the single market, 24.33, times demand in Syldavia, which is 1,500 megawatts. When we have this single market, we have assumed that the flow in the interconnection between Borduria and Syldavia is not limited and would be determined by the market equilibrium, and it turned out that that was 933 megawatts. The total revenue of the generators in Borduria and Syldavia in this case is $48,660 per hour, and that's equal to the total payments by the consumers in Borduria and Syldavia. So you can see that this single market, the amount of money spent on electricity is much lower than it was in the case where we had separate markets, and that's because we have lowered the price by allowing essentially the Borduria generators to compete with the Syldavian generators. The third case is a case where we had a single market with congestion on the interconnection. So we limited the flow on the interconnection to 400 megawatts. So that means that the Bordurian producers could only produce 900 megawatts, 500 megawatts of Bordurian load plus 400 that they export to Syldavia. This meant that the price in Borduria was $19 per megawatt hour, and that their revenue was 17,100, which is 19 times 900. So their revenue is higher than in the case of the separate markets, but lower than the case of the single markets. The Bordurian consumers pay 9,500, which is 19, the price in Borduria, times load in Borduria, which is still 500. This is higher than in the case of separate markets, but lower than in the case of the single market without congestion. In Syldavia, the price in this case is 35, which is lower than the price when we have separate markets, but higher than the case when we have a single market without congestion. The revenue of the Syldavian generators is then 30,500, which is the price, 35 times the production of Syldavian generators, which is 1,100. The Syldavian consumers pay a total of 52,500, which is 35 the price times the demand in Syldavia, which is 1,500. So the Bordurian generators collect more revenue than in the case of a single market, but less than in the case of separate markets, while the Syldavian consumers pay more than in case of the single market, but less than in the case of separate markets. And as I said, the flow between Borduria and Syldavia in this case was limited to 400 megawatts. Now, if we add the revenue of the generators in Borduria and Syldavia, we get 55,600. That is 17,100 plus 38,500. But if we add the total payments by the consumers in Borduria and Syldavia, we get 62,000, which is 9,500 for Borduria and 52,500 for Syldavia. So in this case, as opposed to the other two cases, the total revenue of the generators is not equal to the total payments by the consumers. The difference between these two values is what's called the congestion surplus. Operating this interconnection between Borduria and Syldavia, therefore creates clear winners and losers. On the winner side, we have the Bordurian generators, because they get to produce more and they get to sell at a higher price. And we also have the Syldavian consumers who get to buy the amount of electricity, which in this case we have assumed is not affected by the price, at a lower price. On the loser side, we have the Bordurian consumers who pay more for their electricity, and the Syldavian generators who get to sell less and sell what they have at a lower price. Now overall, if you have a broad perspective of the economy as a whole, the winners or the winnings exceeds the losses. So in terms of the economic performance, this interconnection has a positive effect. Now the difference between the second and the third case suggests that if you limit the flow on the interconnection, or if this flow is limited by congestion, the benefits that you get are limited. So the winners win less, the losers lose less, and overall the economy benefits less. Let's take a more detailed look at this congestion surplus that arose when we put a limit on the amount of power that could flow from Borduria-Syldavia. The consumer payments are given by the price in Borduria, pi b, times the demand in Borduria, db, plus the price in Syldavia times the demand in Syldavia. The producer's revenue, on the other hand, are given by the price in Borduria times the power produced in Borduria, plus the price in Syldavia times the power produced in Syldavia. But the power produced in Borduria is the demand in Borduria plus the flow from Borduria to Syldavia. And the power produced in Syldavia is the demand in Syldavia minus this import from Borduria. So congestion, or sometimes called merchandising surplus, is this E total, what the consumer pay, minus R total, what the generators get. So subtracting the two quantities that we have expressed of and rearranging, we find that this is the price in Syldavia times the difference between the demand in Syldavia minus the production in Syldavia, plus the price in Borduria times the difference between the demand in Borduria minus the production in Borduria, which is the price in Syldavia minus the price in Borduria times the flow between Borduria and Syldavia. If we plot this as a function of the flow in the interconnection, we get this interesting graph where when the flow in the interconnection is zero, meaning we don't have an interconnection or we open the interconnection, the generator revenues and the consumer payments are equal. As we increase the flow in the interconnection, the payments and the revenues decrease, and we decided that was a benefit to the economy, up to the point where the flow in the interconnection reaches the value that would be set by a pure market equilibrium, where again the payments and the revenues are equal. In between, the consumer payments decrease linearly, while the generator revenues decrease faster, and we have this difference between consumer payments and the generator's revenue. Where does this money that comes from this congestion surplus go? Well, in pool trading and centralized trading, it would be collected by the market operator, because essentially it is selling at the higher prices and buying at the lower prices. In this case, it would be selling power in Syldavia at the same price, which is higher than the price in Borduria if we have a congestion on the interconnection. Now, we don't really want the market operator to keep this money, because it gives it a perverse incentive to increase the congestion. because the more congestion there is, the bigger this congestion surplus tends to be. On the other hand, we don't want to return it directly to the network users because that would blunt the economic incentive provided by nodal pricing. In this case, the Bordurian generators are more efficient than the Syldavian generators, so they should have an advantage. And therefore, if we return this congestion surplus to the Borduria and Syldavia, we would remove this incentive for the Bordurian generators to sell in Syldavia. We can't limit ourselves to what is essentially a example. We have to look at what happens when we have loops in our network. So let's move on to a 3-bus example like the one shown on this slide. So we have, in this 3-bus example, we have 4 generators, 2 connected to bus 1, 1 connected to bus 2, and 1 connected to bus 3. We have loads at all 3 buses, and the table on the upper right-hand corner of the slide gives us the reactance and the capacity of each of the branches, and the table on the bottom right gives us the capacity, maximum output of each of these generators, and the marginal costs associated with producing power at each of these generators. So we are assuming very simple cost curves here, linear cost curves, and we can see that generators A and B located at bus 1 are the cheap generators. Generator C at bus 2 is the most expensive, and generator D at bus 3 is in between, but the biggest load is connected to bus 3. How would this work in a market? Well, let's suppose that this market is perfectly competitive, that all generators submit bids that are equal, the price is equal to the marginal cost of production. The total load is assumed constant and is 410 megawatts. Generator B is the cheapest, but can only produce 285 megawatts, so it gets loaded up to its maximum. And the rest of the load is produced by the next cheapest generator, which happens to be generator A. So A produces 125 megawatts, so that the overload is satisfied by production, which happens to be located at bus 1. So we need to calculate then what the flows are going to be in the various lines if we do this economic dispatch. So we need to calculate F12, F13, and F23. So as we did in the our discussion about OPF, we will use superposition in this simple example. So the pattern that we have, where we have a 360 megawatt net injection at bus 1, that's the production of these 2 generators minus the load at bus 1. We have an extraction of 60 megawatts at bus 2. That's because we have a load of 60 megawatt at bus 2 and no generation at bus 2. And we have an extraction of 300 megawatt at bus 3 because we have a 300 megawatt load at bus 3, and generator D is not producing anything under this economic dispatch. So we're going to use superposition, so that means we're going to say that this overall pattern is the sum of the pattern that would result from injecting 300 megawatts at bus 1 and extracting 300 megawatts at bus 3, and an injection of 60 megawatts at bus 1 and extraction of 60 megawatts at bus 2. So this is a good exercise for you to remind yourself how to do a simple flow calculation assuming superposition. The solution is given on the net. And here's the solution. We have 156 megawatts flowing from bus 1 to bus 2, 204 megawatts flowing from bus 1 to bus 3, and 96 megawatts flowing from bus 2 to bus 3. Now there's a problem with this economic dispatch and the flows that it creates, in that the flow between 1 and 2 is 156 megawatts, while the maximum allowed flow on this line is 126 megawatts. So if the market tries to implement this economic dispatch, the system operator will not accept it because it's not a solution. To correct this problem, we could increase the generation at bus 2 or increase the generation at bus 3, and therefore reduce the generation at bus 1 by the corresponding amount. So if we increase the generation at bus 2 by 1 megawatt, while reducing the generation at bus 1 by 1 megawatt, so that corresponds to an injection of 1 megawatt at bus 2 and extraction at 1 watt at bus 1, because we are assuming the system is linear, because we are doing a DC power flow approximation. 0.6 megawatts will flow directly from 2 to 1, while 0.4 megawatts will flow from 2 to 3 to 1 because of the relative reactances of the branches in this system. So if we want to correct this 30 megawatt overload in the line from 1 to 2, we need to create a counterflow of 30 megawatts from 2 to 1. And because for each megawatt injected at bus 2 and extracted at bus 1, only 0.6 megawatts flows directly from 2 to 1, we have to inject an extra 50 megawatt at bus 2 and reduce the output of generators at bus 1 by 50 megawatts. So on the bottom right hand corner of this slide, you see flows that would result from this dispatch, and we would therefore be producing only 310 megawatt at bus 1, and we would have a net extraction of 10 megawatts at bus 2, that's 60 megawatt loads minus the 50 megawatts additional generation at bus 2, and we would still have a load of 300 megawatts at bus 3. The other solution is to inject more at bus 3, meaning generating more with generator D and generating less with the generators at bus 1. Now again, if we inject an extra megawatt at bus 3 and extract it at bus 1, we are going to have 0.6 megawatts flowing directly from bus 3 to bus 1, while 0.4 megawatts flow from bus 3 to bus 2 to bus 1. So, to correct the 30 megawatt overload in line 1, 2, in this case, we need to again to create a counterflow of 30 megawatts between 2 and 1. And because of the way the injections at bus 3 divide themselves, that means we need to inject 75 extra megawatts at bus 3, extract an extra 75 megawatts at bus 1 to get a 30 megawatt counterflow flowing from 3 to 2 to 1. And the result of this change to the dispatch using superposition is that we would be having a net injection of 285 megawatt at bus 1. We would have an extraction of 60 megawatt at bus 2, that's just the load at bus 2, and a net extraction at bus 3 of 225 megawatt, which is the 300 megawatt load at bus 3 minus this 75 megawatt injection at bus 3 by generator D. Now, to find the solution that we are going to implement, we have to look at the cost of these dispatches. The cost of the economic dispatch was $2,647.5 per megawatt hour. If we redispatch generator 2, the total cost is going to be $2,972.5 per hour. But on the other hand, if we redispatch generator 3, the total cost is going to be $2,835 per hour. So redispatching generator 3 is better than redispatching generator 2, and that's what we are going to do. Note that in this case, the cost of security is the difference between the cost of the dispatch that does not overload line 1 and the cost of the economic dispatch, and in this case it's $187.5 per hour. So this figure shows the security constraint dispatch, showing that we now have 126 megawatts flowing from bus 1 to bus 2, which is just the maximum allowed in this line. We have off the generation from generator A, because it's the more expensive of the two generators connected at bus 1. So A is now producing 50 megawatts and B is still at its maximum of 285 megawatts. Generator C still produces nothing, and generator D is now producing 75 megawatts to create the counterflow that was necessary to reduce the flow in the line 2. So now we know what dispatch the market should implement to achieve the lowest overall cost or maximum global surplus. But what we need to calculate next are the nodal prices, which indicate what generators would be paid for producing at each node and what consumers should pay at each node to consume power. And we will do this by going back to the definition of the nodal price, which is the cost of supplying an additional megawatt of load at a particular bus without violating the security constraints. And to do that, we'll start from the security constraint dispatch, which is the dispatch that the market will implement. Let's consider each node in turn, and let's start with node number 1. Now, to calculate the nodal price, I need to add 1 megawatt of load at node number 1. But if I add 1 megawatt of load at node number 1, this megawatt would be produced by generator A, because generator A is the cheapest generator in this case, the marginal generator, and because extra megawatt of load is located at bus 1, it would not get into the network, so it would not cause any problems in the network. So conclude that the marginal cost of supplying 1 megawatt of load, 1 extra megawatt of load at bus 1 is $7.5 per megawatt hour, which is the marginal cost of producing it with generator A, and we're going to say that is the nodal price at bus 1. How about bus 3? Well, if we add a megawatt of load at bus 3, we would probably want to try to produce it with the cheapest generator, which would be generator A, because generator A is cheaper than generator D or even generator C. But if we increase the output of generator A by 1 megawatt, some of this megawatt would go over line 1, 2, which is already operating at its maximum capacity, so it would overload line 1, 2. So we need to produce this megawatt somewhere else. Could produce it with C, but D is cheaper, so the answer is we would produce it with D. So the nodal price at bus 3 is the marginal cost of producing 1 megawatt with generator D, which is $10 per megawatt hour. How about node 2? Well, if we add the megawatt of load at node 2, we could produce it with generator C, but generator C is very expensive. So let's see if there are other solutions. If we produce with A, an extra megawatt with A, some of it is going to flow on line 1, 2, and that's not going to be acceptable. Same thing if we produce a megawatt with generator D. Well, it could flow, some of it would flow from 3 to 1 to 2 and would also overload line 1, 2. So these two solutions taken separately are not going to work. And at first glance we think, okay, we have to produce it with C. But in fact, there's another way to deal with it. So let's see what happens if we inject an extra megawatt at bus 1 and extract an extra megawatt at bus 2. We have 0.6 megawatts flowing from line 1, 2, and 0.4 going from 1 to 2 via 3. If we do the same thing but inject a megawatt at bus 3, we have 0.2 megawatt flowing from 3 to 1 to 2, and 0.8 megawatts flowing from 3 to 2. So you can see that the flow that goes through line 1, 2 is not the same if we add a megawatt at bus 3 or add a megawatt at bus 1. So what we could do is combine an extra injection at bus 3 and a reduction in the injection at bus 1 to try to keep the flow in line 1, 2 constant. So let's try to be a bit formal about this. What we want to achieve is a delta P2 of 1 megawatt at bus 2. And we want to achieve it by having a delta P1 at bus 1 and a delta P3 at bus 3. But overall, we want a delta F12 that is equal to 0. We want to keep the flow on line 1, 2 at exactly its upper limits. So what we want is delta P1 plus delta P3 must be equal to delta P2, which is 1 megawatts. And we want a delta F12 which is equal to 0. But delta F12 is a result of 0.6 times delta P1, the fraction of the megawatt that goes on line 1, 2, plus 0.2 times delta P3, the fraction of an extra megawatt injection going on line 1, 2. So we have a system of two equations in two unknowns, delta P1 and delta P3, we can solve. And if we do that, we get that delta P1 should be minus 0.5 megawatts, and delta P3 should be 1.5 megawatts. That means that if we want an extra megawatt of load at bus 2, we would have to increase the injection at bus 3 with generator D by 1.5 megawatts and decrease the injection at bus 1 from generator A by half a megawatt. So the cost of this extra megawatt of load at bus 2 would be 1.5 times the marginal cost of production with unit D, that's the extra cost, minus 0.5 the marginal cost of producing with generator A, because that's the saving resulting from the decrease in production with generator A, and that would give us $11.25 per megawatt hour. We can make several observations based on this 3-bus example. First, generators A and D are marginal generators because if you add a megawatt of load at the bus where they are connected, it will be produced by these two generators. On the other hand, generators B and C are not marginal generators, B because it's at its upper limit, and C because it's turned off. So in an unconstrained system, we had one marginal generator. But if we have a system with M constraints, we will have M marginal generators. So in this little 3-bus example, we had one line that was operating at its upper limit, so we had one point, and therefore we had two marginal generators. Finally, the prices at the nodes where there is no marginal generators are set by a linear combination of the prices at the other nodes. So this table summarizes what happens in our 3-bus system. First line shows the consumption in megawatt at each bus in the system and in the system as a whole, how much power is produced at each of these buses, the nodal marginal price, and as you remember, at bus 1 and bus 3, it's given by the marginal cost of producing power with a generator connected to these buses, but that generator 2, it is a linear combination of the marginal costs at other buses. The next line gives us the consumer payments in dollars per hour. That's given by the price at the node times the consumption at that node. And the next line is the producer's revenues, which is given by the amount that these producers produce times the nodal price that they are getting for their production. So there is no producer revenue at bus 2 because generator C is not producing anything. So in the last column we summed the consumer payments over the whole system and the producer's revenues, and we see these two quantities are not equal. So in this 3-bus example, we also have a merchandising or congestion surplus, which turns out to be $787.5 per hour. If we look at this diagram where we have plotted the flows and indicated the prices at each node in our 3-bus example, we can see that there's something a bit funny going on here. The flow in the line between bus 2 and bus 3 is 66 megawatts. What's interesting is that the price at bus 2 is $11.25 per megawatt hour, while the price at bus 3 is only $10 per megawatt hour. That means that we have a flow from a high price bus to a low price bus. So we have a commodity that flows from a place where the price is high to a place where the price is low. Now that is contrary to the laws of economics, which would say that normally commodities should be produced in places where they are cheap and sold in places where they are expensive. But in this case, these, between quotes, laws of economics are superseded by Kirchhoff laws or the laws of physics. Funny things can also happen with prices. They can be counterintuitive. For example, prices at nodes without a marginal generator can be higher or lower than prices at the other nodes. In our 3-bus example, we found out that prices at bus 2 was higher than the prices at bus 1 and 3. But in some cases, nodal prices can even be negative. That has been observed not only in simple examples, but also in real-life electricity markets that implement nodal prices. So the nodal prices, we need to calculate them. We can't just predict them on looking at how the market is going. And also, a strategically placed generator will be able to control prices because this network congestion helps these generators exert market power. Let's now turn our attention to the effect that losses might have on nodal prices. And let's do that using a simple example again with 2 buses. We have a generator at bus 1 that produces power G and a load at bus 2 which is equal to D. The variable losses in the system are the I squared R losses, but I is S over V, and S being the complex power is square root of P squared plus Q squared, so S squared is P squared plus Q squared. Now typically the active power flowing in a line is much larger than the reactive power flowing this line, so we'll make the assumption that we can neglect Q squared, and therefore our variable losses are given by R over V squared times P squared, or some factor K times P squared, where K is R over V squared. We will neglect the changes in voltage. Now the generator G must produce a certain amount of power to meet the demand D, and this generation must be equal to demand D plus whatever losses we have. So G of D is D plus K times P squared or D squared in this case. Now if the load increases by a delta D, we have a delta G of generation. This delta G is going to be of power that needs to be produced to meet D plus delta D minus the amount of power that needs to be produced to meet the demand D. And that turns out to be equal to 1 plus 2 times the demand D times factor K times the delta D. Now, using this extra power increases the cost by factor delta C, which is little c, the marginal cost of producing power with generator G, times 1 plus 2D times K times the increase in load delta D. So the marginal increase in cost resulting from a marginal increase in demand delta D is C, the marginal cost of producing power at bus, times this factor 1 plus 2D times K. So in this system, if we don't have congestion, but we consider the losses, the marginal cost of producing power at bus 1 is equal to the price at bus 1 will be little c, while the price at bus 2 is the marginal cost of producing power for an increase of load of 1 megawatt. Bus 2 will be c times 1 plus 2 dk, or pi 1 times 1 plus 2 dk. So this losses in the line between 1 and 2 create a price difference between bus 2 and bus 1. Let's go back to our example Borduria-Syldavia to see how it might be affected by losses. The power produced in Syldavia, PS, is equal to the demand in Syldavia minus the power imported from Borduria, FBS. On the other hand, the power produced in Borduria is equal to the demand in Borduria, DB, plus what gets exported to Syldavia, FBS, plus the losses on the line between Borduria and Syldavia, which we'll assume are this factor K times FBS squared, the square of the power flowing from Borduria to Syldavia. Now, if we plot the total generation cost, so that's the cost of producing PS and producing PB, where PS is accounted for with the cost in Syldavia and PB is accounted for as a cost in Borduria, we saw that the amount that should flow through the line went through a minimum around 933 megawatts. That's a flow that would result in a market equilibrium when we neglected losses, and that was the minimum generation cost. We include the losses, we see that this minimum occurs for about 848 megawatts, and that's due to the impact of the losses that increase the amount of the cost of producing power in Borduria. So far, our explanation of nodal pricing has been relatively ad hoc. At this point, we turn our attention to a more mathematical formulation. And the reason for this is that the independent system operator is going to need a systematic method to calculate these prices. Now, this is going to be a constraint optimization problem where the objective is to maximize the global welfare, and the constraints come from the operation of the network. Now, in this calculation, we assume that we have perfect competition. Let's start with a one-bus system where the network is trivial. In this one-bus system, D will represent the total demand from the consumers, P will represent the total production of the generators, B of D will represent the consumer's benefit function, the value that the consumers get from electrical energy, C of P will be the producer cost function, and the global welfare will be the difference between B of D and C of P. So our objective is going to be to maximize the global welfare, or the difference between B of D and C of P, subject to, in this case, a single constraint that the load must be equal to the generation, or P minus D must be equal to 0. In this one-bus network, our Lagrangian function is a function of three variables: the demand D, the power produced P, and a Lagrange multiplier, which we'll call pi for reasons that will become obvious. And this Lagrangian is given by objective function, B of D minus C of P, plus pi, the Lagrange multiplier, times P minus D. As usual, we can write the optimality conditions by taking the partial derivatives of the Lagrangian with respect to all the variables. So we get dl over dd is dB over dd minus pi equals 0. dl over dp is minus dc dp plus pi equals 0. And dl over dpi is simply the constraint, p minus d equals 0. Putting the first two optimality conditions together, we get that dB over dd should be equal to dc over dp and should be equal to pi. That means that the consumption and the production should increase up to the point where the marginal value of electricity to the consumers is equal to the marginal cost of this electricity of producing this electricity, and is therefore equal to the price at which this electricity should be sold. Let's move on from this very simple case to something a bit more sophisticated. Let's suppose that we have a network of capacity, so therefore a network where we won't have any congestion, but a network where we have losses. And in this case, we want to define the net injection at bus k, Ik, and that's going to be equal to Pk, the power produced at that bus, minus Dk, the power consumed at that bus. And the network creates economic welfare by allowing trades between nodes with positive injections and nodes with negative injection. And we will represent this welfare by Wk of Ik. And if I is negative, that means we have an extraction or a load that represents the benefits of consumers at node K. On the other hand, if Ik is positive, meaning we have an injection or a generation at bus K, Wk of Ik represents minus the cost of producers at node K. And if we sum this over all the nodes in our network, big W is the sum from k equals 1 to n of Wk of Ik, we get the global welfare created by this network. Now, what we want to do is maximize this welfare. So we want to choose the injections Ik at the various nodes in such a way that W is maximum. So we want to maximize over Ik the sum from k equals 1 to n, where n is the number of buses, of Wk of Ik. But we can formulate that in a different way, because if we want to maximize W, well, it's the same thing as minimizing minus W. So we would be looking at minimizing over the injection Ik the sum from k equals 1n of minus Wk of Ik. And if we assume that the demands are insensitive to prices and that the loads are constant and therefore that the consumer's benefits are constant, what we can say is that means we're neglecting the Wk's at the load buses, then minimizing minus the welfare is equal to minimizing over injections the sum from k equals 1 to n of the cost of producing injection k at bus k. And that is equivalent to an economic dispatch or an optimal power flow. So, we want to minimize the sum from k equals 1 to n of Ck of Ik by choosing these injections Ik. That's objective functions. What about our constraints? Well, we have assumed that we don't have network congestion because we have assumed a network of infinite capacity. So what we have to impose as constraint is that the total generation should be equal to the total load plus the losses. Or more specifically, that the net injections are equal to the total losses in the branches of the network, because the rest of the injections match the generation and the load. So mathematically, what we want is that the sum from k equals 1 to n of ik is equal to the losses. Now, note that I have expressed the losses as a function of the injections from bus 1 to bus n minus 1, because I assume that bus n is the slack bus and is therefore the bus that is going to make sure that these losses are met. So we can form a Lagrangian for this optimization problem. It's equal to the objective function, sum from k equals 1 to n of ck of k, plus the Lagrange multiplier pi times the difference between the losses and the net injections. The optimality conditions are obtained by taking the partial derivatives of this Lagrangian with respect to the injection, first set of optimality conditions. I treat separately the partial derivative with respect to the injection at node n. And the last optimality condition says that the partial derivative of Lagrangian with respect to the Lagrange multiplier pi is essentially the constraint, must be satisfied. So if I take the first two sets of optimality conditions, I conclude that dck over ik for all k from 1 to n minus 1 must be equal to dcn over in times 1 minus dl over dik, which is equal to the price, or Lagrange multiplier pi, times 1 minus dl over ik. So let's look at that. It shows that the nodal price at bus k, dck over dik, is related to the nodal price at the slack bus, dcn over din, or pi. And the relations involve 1 minus dl over dik. So if dl over dik is positive, we will have that dck over dik will be less than dcn over din. Now, what does that mean? Well, it means that if the injection at bus k increases the losses, dl over dik is positive, the price at bus k will be less than the price at the slack bus. That means that the generators will receive a lower price at bus k than they would at the slack bus, and that consumers would be paying a lower price at bus k than they would at the slack bus. Essentially, it penalizes the generators for producing at a bus that increases the losses and encourages consumption at a bus where reducing the injection, so increasing the load, would reduce the overall losses in the system. In this case, reducing the losses increases the global welfare. Let's move on to the case where our network has only a finite transmission capacity. That means that we're going to have some limits on what the line can carry. So for example, line L, which is one of m lines in the system, the flow on line L is a function of the injections that all buses except the slack bus should be less or equal than the maximum flow on that line. So our Lagrangian, we have to add a term, so it has the standard cost function of the injection plus pi times the constraint we had before that related the losses and the net injection at all the buses. And then we have an additional constraint for each constraint on the line flows. So FL max minus FL of IN minus 1. We multiply that by a Lagrange multiplier mu L, and we have one of those for all the M lines in your system. I've repeated the Lagrangian function for this problem at the top of this slide, and we can move on to the optimality condition. Take the partial derivatives with respect to the net injections at buses K, which with K going from 1 to n minus 1, gives us our first optimality conditions. It involves the derivative of the cost of producing power at bus K with respect to IK, pi times dL over dIK minus 1, and then we have minus mu dFL over dIK, where dFL over dIK indicates how the flow in line L is influenced by the injection at bus K, and that must be equal to 0. The partial derivative of the Lagrangian with respect to the injection at the slack bus, which is bus N, is a bit different because we are not including the injection at the slack bus in the expression for the losses or expression for the flow in line L, otherwise we would get an indeterminate system. So dL over din is dCn over din minus pi. The partial derivative with respect to pi is simply the constraint expressing that the losses must be equal to the sum of the net injections at all the buses. And the partial derivative with respect to mu L is the constraint on the flow in line L. And finally, we have the complementary slackness condition for each of the constraints on the line flows, which tells us that this constraint, each of these constraints, is either binding or non-binding. Instead of considering an arbitrary number of binding constraints, let's assume that only line I is congested. So using the complementary slackness conditions, we conclude that mu I is going to be greater or equal to 0, while all the other mu j's are going to be equal to 0. If we introduce this in the optimality condition, we get that dck over dik equals pi 1 minus dl over dik plus mu I dfi over dik for all buses from 1 to n minus 1. At the slack bus, we still have dCn over din equals pi. We have that the losses are equal to the net injections, and that the flow in line I is equal to the maximum flow in I. Now, the important thing to notice from these equations is that in the first optimality condition, we have this term mu I dfi over dik, which means that the price at all the buses, except the slack bus, is going to be affected by the fact that there is congestion in one line. It's because the flow in that one line is affected by the injection at every bus. Let's see how we can take this analysis further by making the assumption that we can model the network using a DC power flow model. So the DC power flow model relates the injections at each bus to the voltage angles at each bus using the admittance matrix. So in particular, II, the net injection at bus I, is equal to j sum from j equals 1 to n of yij theta I is theta j. The line flows in this DC model, for example, the line flow between lines I and j, Fij, is equal to Yij theta I minus theta j. Therefore, the line flow constraints can be expressed as Yij theta I minus theta j less or equal to Fij max for all I and j. And that means we can get a slightly different Lagrangian function where we have the Lagrangian equal to the sum from I equals 1 to n of Ci of II. That's the cost of injection at each bus in the system. The equality constraint, each equality constraint being multiplied by a Lagrange multiplier pi I. So that's sum from I equals 1 to n of pi I times I minus sum from j equals 1 to n of Yij theta I minus theta j. And then we have the inequality constraints on the line flows. Well, we're treating these as given by for each bus, so we have a sum from I1 to n, a sum from j equals 1 to n of mu ij for the flow on the line linking buses I and j, Fij max minus Yij theta I minus theta j. Having built this Jacobian, we can, as usual, develop the optimality conditions by taking the partial derivative of the Jacobian with respect to the injections, with respect to the state variables, the voltage angles, and with respect to the Lagrange multiplier pi I, and with respect to the Lagrange multiplier mu ij. And we also add the complementary slackness conditions. These optimality conditions give us a set of equations that we can solve to find these prices and shadow prices. First, we observe that if we have m binding constraints, we will have m plus 1 marginal generators. Now, the prices of buses where these generators are connected can be determined using the equation dci over dii minus pi equals 0, because this partial derivative is known at bus I if bus I is a marginal generator. So that gives us m plus 1 known price pi I. That leaves us with n minus m minus 1 unknown prices and m unknown Lagrange multipliers mu ij. And we'll use the second optimality conditions to determine these prices and shadow prices. This second set of optimality conditions gives us n minus 1 equations that we can use to solve for the n minus m minus 1 unknown nodal prices and the m Lagrange multipliers mu. To solve these equations, we might want to separate the buses into two sets. The set K of the buses where the price is known because there is a marginal generator connected to this bus, and the set U, the set of buses where the price is unknown. Then we can group the equations obtained from the second optimality conditions into the two sets so that we have on the left-hand side the unknown variables and on the right-hand side the known variables. To take an example of how this might work, let's go back to our 3-bus example under the conditions that we considered. As you may recall, we found that generators A and D were marginal, so we have marginal generators at buses 1 and 3. Therefore, the price at bus 1 is given by the marginal cost dCA over dPA, which is $7.5 per megawatt hour, and the marginal cost of generator D gives us the price at bus 3, dCD over dPD is $10 per megawatt hour. On the other hand, the price at bus 2 is unknown, and the line between buses 1 and 2 was also an active constraint, so the Lagrange multiplier mu12 is unknown. So we have two unknowns, and in terms of the sets of buses, the set K of buses where the price is known is the set 1, 3, and the set U where the price is unknown is a singleton 2. The next thing we need to do with this example is choose a slack bus. This choice is arbitrary, but slack bus should be a bus where there is a marginal generator. So we will choose bus 3. Now we bring in the conditions that we wrote for finding the unknown prices and unknown Lagrange multipliers. And the first set corresponds to the equation that have been written for the buses where the bus is in the set where the price is unknown. In this case, that corresponds to bus 2. So this is the equation that we get when we write it for bus 2. And then we have another equation that we can write for bus 1, but bus 1 belongs to the set of buses where the price is known. So this is the equation that we get for bus 1. So on the left-hand side of these two equations, we have pi 2 and mu 1, 2, which are the unknown variables. And on the right-hand side, we have pi 1 and pi 3, which are the known prices. These equations involve terms coming from the admittance matrix of this network. So we need to build this admittance matrix, and to do that we go back to the table that was giving us the reactance of the branches of this network. The off-diagonal terms of the matrix Y, the admittance matrix of this network, are given by the admittances of the branches. So if the reactance is 0.2, the admittance Y12 will be 5, and same thing for Y13, and Y23 will be 10 because the reactance is 0.1. Terms Y21, Y31, and Y32 are obtained by symmetry. The diagonal terms are minus the sum. So if we go back to the equations we wrote for this system, and introduce the values from the admittance matrix, these equations turn out to be 5 pi 2 minus 5 mu 1 2 equals 25, and minus 15 pi 2 plus 5 mu 1 2 equals 137.5. If we solve these equations, we get that pi 2 is $11.25 per megawatt hour, and mu 1 2 is $6.25 per megawatt hour. Now the value of pi 2 matches the one that we found by the ad hoc method we used to introduce the concept of nodal prices. The value of mu 1 2 gives us the shadow cost associated with this constraint. So it means that if we relax the constraint by 1 megawatt, we will save $6.25 per hour. On the other hand, if we tighten this constraint by 1 megawatt, well, it will cost us an extra $6.25 per megawatt hour. In our last section, we will consider what's called financial transmission rights. And financial transmission rights are designed to help users manage transmission risks. Because as we have noticed, congestion and losses affect the nodal prices. Therefore, they represent an additional source of uncertainty and therefore risk for market participants. And as we know, market participants are always looking for ways of avoiding or reducing risks. And they need some financial instruments to help them deal with this nodal price risk. So one way to try to deal with this would be contracts for difference. Because, as you remember, in the centralized market that we are dealing with, the producers must sell at their nodal price and the consumer must buy at their nodal price, and they may be selling at different nodes, therefore they may be facing different nodal prices. So they have to sell in a physical market or buy in a physical market, but they are also allowed to enter into bilateral financial contracts, which we could call contracts for difference. So let's take an example of a contract for difference. Let's go back to a Borduria-Syldavia example, but instead of looking at the market as a whole, let's consider two participants in this market. Borduria Power, a generator located in Borduria, and Syldavia Steel, a large consumer located in Syldavia. And let's suppose that these two participants have entered into a contract for difference for 400 megawatts, and they have agreed on a strike price of $30 per megawatt hour. Now, I'm only considering these two participants, but other participants in this market are also using the interconnection between Borduria and Syldavia. Let's first consider the case where there is no congestion on this interconnection between Borduria and Syldavia. Therefore, we have the same price in Borduria and in Syldavia, and let's suppose that it is $24.30 per megawatt hour. So, let's see how the contract works. Borduria Power sells 400 megawatts at 24.30 and gets 9,720. Syldavia Steel buys 400 at 24.30, which is its nodal price, and therefore pays 9,720 in the centralized market. Syldavia Steel has a contract for difference with Borduria Power, and since they have agreed that the strike price was 30, which is higher than 24.30 that Syldavia Steel paid in the market, Syldavia Steel owes 2,280 to Borduria Power. Therefore, Syldavia Steel's net cost is 9,720 plus 2,280, which is $12,000. And similarly, Borduria Power's net revenue is also $12,000. So these two participants have effectively traded 400 megawatts at $30 per megawatt hour. Let's now consider a case where there is congestion on the interconnection between Borduria and Syldavia. And as a result of this congestion, the price in Borduria is $19 per megawatt hour, while the price in Syldavia is $35 per megawatt hour. What happens to a contract? Well, Borduria Power sells 400 at 19 and gets 7,600 from the centralized market. Syldavia Steel buys 400 at 35 and therefore pays $14,000 in the centralized market. Now, Borduria Power has this contract for difference with a strike price of 30 with Syldavia Steel. And because it only got 19 in the centralized market, it expects to get 400 times 30 minus 19 from Syldavia Steel. Syldavia Steel also has a contract with Borduria Power with the same strike price, and therefore it expects to get 400 times 35 minus 30 because it paid 35 in its centralized market and the strike price of the contract for difference is 30. So it expects to get $2,000 from Borduria Power. Now obviously we have a problem here because there's some missing money. There's a shortfall of 6,400. And the conclusion of this is that a basic contract for difference is going to break down if we have nodal pricing and if the different participants are seeing different prices. That's why financial transmission rights were invented. So, how do they work? Well, let's start with some observations. First, let's observe that the shortfall in the contract for difference is equal to the congestion surplus. This congestion surplus is collected by the system operator. But as we said earlier, we should not allow the system operator to keep this congestion surplus because it would give it a perverse incentive to increase congestion in the network, which is not economically desirable. So the concept of financial transmission right is that the system operator is going to sell financial transmission right to the users of the network. And these financial transmission rights are essentially a contract between the system operator and the users. And if I purchase a contract for a financial transmission right contract for F megawatt between Borduria and Syldavia, this contract entitles me to receive from the system operator F times the price difference between Syldavia and Borduria. And that makes me, as a holder of financial transmission right, indifferent about where I'm trading energy. Now, on its side, the system operator is collecting exactly enough money in congestion surplus to cover the payments to holders of financial transmission rights. So let's see how this might work in our example. Let's suppose that Borduria Power and Syldavia Steel have a contract for 400 megawatts. They have agreed that it would be delivered in Syldavia, and the strike price is $30 per megawatt hour. Now, because Borduria Power is exposed to locational price risk, is going to purchase 400 megawatts of financial transmission right from the system operator. So, let's suppose that the price in Borduria is $19 per megawatt hour. The price in Syldavia is $35 per megawatt hour. Borduria Power sells 400 at 19 and therefore gets 7,600. Syldavia Steel buys 435 and therefore pays in the centralized market $14,000. The system operator collects 400 times the price difference between Borduria and Syldavia, that's 35 minus 19, or $6,400 in congestion surplus. Borduria Power, because it has bought these financial transmission rights from the system operator, is going to collect 400 times 35 minus 19, $6,400 from the system operator. Borduria Power is going to pay Syldavia Steel 400 times 35 minus 30, or $2,000, to settle the contract for difference that they have agreed on. So Syldavia Steel net cost will be $12,000, which is $14,000 that it pays in the centralized market, minus the $2,000 it got from Borduria Power. And Borduria Power will net revenue is going to be $12,000. That's $7,600 from the centralized market at Borduria price, plus $6,400 from the financial transmission right, minus $2,000 that it paid to Syldavia Steel to settle the contract for difference. So the conclusion is that the books balance. There is no missing money. The financial transmission right make the transaction possible. So financial transmission rights therefore provides what's called a perfect hedge against variations in nodal prices. Now, the system operator should auction transmission rights for the maximum transmission capacity of the network. If the system operator sells more transmission rights than the amount of power that it can deliver, it's going to lose money because it will not be able to deliver. It will not get enough congestion surplus to cover these transmission rights. Now, the proceeds from this auction will help cover the investment costs of the transmission network. And this auction does not give the system operator a perverse incentive to increase congestion because they have no bearing on the amount of congestion that's going to happen. However, on the user side, they have to estimate the value of these transmission rights that they buy at auction. Now, financial transmission rights are defined from point to point. That means that it doesn't need to have a direct branch connecting the points between which the FTRs are defined. In our Borduria-Syldavia example, there is a direct connection, but it doesn't really matter if there's such a connection, because these FTRs automatically factor in the effect of Kirchhoff's voltage law. Now, not everything is easy with financial transmission rights. There are many possible combinations of point-to-point transmission rights, and it's going to be difficult to assess the value of all the possible rights, and therefore setting up a market for point-to-point transmission rights is going to be somewhat difficult. So some people have suggested that instead of having point-to-point financial transmission rights, we should have instead, or in addition, flow-gate rights. And flow-gate rights start from the observation that typically only a small number of branches are congested. And the idea is that users would buy transmission rights only on those lines that are congested. And theoretically, it can be shown that it is equivalent to point-to-point rights. The advantage is that you would need to trade fewer rights because you would only need to trade on the rights on the branches that are congested. And that would lead to a more liquid market in flow-gate rights. The difficulty is that you would have to identify ahead of time which branches are likely to be congested. And as the system configuration changes because of maintenance, that may be difficult to do on a systematic basis.